We have most of the presenters, and we can start. Let me. So, hello everyone, and welcome to the second track of day one at the BTR conference. My name is Fatima Mostafa. I'm an assistant professor at the University of Connecticut. And I will be moderating this session, which is about transportation data analysis and modeling. In this session, we will have 6 presentations. Each presenter has about 15 to 18 minutes time to present, and we will have 2 minutes for question and answers. So our first presenter is Phillip Ayebare. Phillip is a master's student in civil engineering at the University of Texas at Austin, working with Dr. Kara Kockelman. He currently works at the Alliance Transportation Group as a transportation modeler too. His research focuses on shared autonomous vehicle fleet operations via activity-based models, and he's passionate about building and utilizing travel demand models to forecast travel patterns. Phillip will be presenting his research on fleet profitability and other performance metrics across days of the year. Phillip, floor is yours. You can share your screen and start your presentation.
Thank you. Thank you, Fatima. Can you hear me?
Yes, we can hear you, but we cannot see your screen.
Okay, let me share my screen now. Can you all see my screen now?
Yes, we can see.
Okay, so thank you for coming to my presentation. I'll be speaking on shared autonomous vehicle operations and day-to-day demand variation in the Dallas-Fort Worth region. So as a bit of a background, the DFW region consists of 11 counties, over 10,000 square miles with 7.5 million residents, making 25 million one-way person trips, and with 23.4 auto person trips per person per day, and an average of 6 miles, an average trip distance of 6 miles. This area is really large, quite large, with 5,000 TAZs and so many nodes, about 42,000 links and 28,000 nodes. So in this region, we combined RITIS plus NHTS data and applied and used those trips in our agent-based model called Polaris in order to appreciate fleet operators' financial perspectives and also look into SAV fleet performance metrics. And so we assumed in the model that we provided 1 SAV for every 40 residents, and also assumed fares of a $1 base fee, 50 cents per mile and 25 cents per minute for each SAV, with operating costs of over 50 miles, 50 cents per mile, and $25 per SAV per day. And 7% fixed demand was assumed as well. This was based on the RITIS strips that were sampled at the rate of 7%. And while external trips were added to add congestion to the network, the external trips were provided by the Metropolitan Planning Organization of the Dallas region, NCTCOG. And these external trips included light, medium, and heavy duty trips. And then the SAV module in the Polaris model was extended to incorporate and implement party size constraints for shared trips. Default dynamic ride sharing algorithm was also utilized, and a trip party size of 1.6 was realized. And so I'll speak more to the data sources. The RITIS platform was used to generate OD matrices the RITIS platform typically uses INRIC's trip path, the INRIC trip path dataset. And the RITIS trips, like I'd mentioned before, represent 6 to 8% of light-duty vehicle trips. And that's why we were only able to serve 7% demand. And then the RITIS trips were modified to include 20% of SAV mod splits. And different dates of these trips were sampled on different dates of a year, different dates across the year. And one of the limitations we faced, of course, was there was limited availability of data, as we could only sample trips from the months of April, March, and November, October, and November. So tried as much as possible to sample trips on days that are representative of typical work days and school days and holidays as well. And so this RITIS platform dataset just includes a complete pathway of trip within a specified base geography. The specified base geography being the Dallas-Fort Worth region, and filter settings. Within the platform, there's filter settings that enable you to extract the trips with similar characteristics. And so the distribution of these long distance vehicle trips is shown here. We can see that the evening peak from 12 a.m. to 6 a.m. and the AM peak from 6 a.m. to 9:30 a.m. The midday peak off peak from 9:31 a.m. to 2:59 p.m. as well as the PM peak from 3 to 6:30 and the late night peak from 6:31 to 11:59 p.m. We can see that the AM and PM peaks comprise 3.5 hours, while the off peaks comprise 6 hours. And most of the trips were made during the midday and the PM off peaks. So here we have the RITIS sample VMT values. So after sampling days from the RITIS platform or trips from the RITIS platform across these different days, we typically notice that there is a larger sample of the trips has about 1.3 million vehicle trips per day on average that start and end within the region across these days. And then you can see that the trip data sample had clustered values around the mean. So the mean here was 31.64 as a mean, and most of our values are clustered around this value. And so in order to kind of get an understanding of the distribution of trips across the year, we use the NHTS dataset for just the DFW region. So the DFW or the person trips from the NHTS dataset. This dataset was filtered, to retain days on which there was more than 30 respondents surveyed, and then we remained with 190 days out of 372, and within these 190 days, we're able to get 10 decile days. So basically splitting is 190 days into 10 clusters, each 10 clustered days, and then finding the decile value of each of these clusters. Then this table shows the NHTS dates that we were able to filter from the table, together with the number of persons sampled and the VMT on each of these days. We believe this data set is more representative of travel across the whole year. And so that's why it was applied to the RITIS data set that wasn't really representative of travel across the whole year. And so the Z-score was calculated from that table that I just showed you in the previous slide and was used to determine the scaling factor that was applied to these RITIS trips. And so now from the scaling, we see the scaled VMT values and the previous RITIS values from the RITIS dataset. And so these scaled values, of course, these are averages, but the new total trips after scaling were added to the Polaris demand database, and this is just a distribution of the trips that were scaled and where they lie in terms of VMT per capita per day. Of course, in the end, we didn't get a representative distribution of trips. We would prefer to have trips lying within the 5th decile or lying closer to 5th decile to the 95th. 5th percentile to the 95th percentile, but most of the trips lie between the 50th percentile to the 95th percentile, although there's a little bit more spread compared to the RITIS trips. So the values that we see here are the scaled values, although, sorry, this is an error. The RITIS VMT values in the legend is an error. It's supposed to be scaled VMT values. So yeah, these total trips were then added to the Polaris, the agent-based model, and the simulations were ran to kind of understand, as I said in the beginning, to understand how the SAVs are going to perform, and how much profit the operators are going to earn on, to be representative across these different days of the year. And so here we see the day-to-day variation results. We see the profit per SAV per day ranges between $74 to $124. We also saw that profit per mile maintained relative consistency between $0.18 to $0.24. So this, the highest value was realized on a typical work day. In this case, we see 26th of May, 2016. Typical work day during the spring, could be a school day as well. But on the opposite side of the spectrum, we see that the 24th of November was a Thanksgiving holiday. And that's where the least profit was realized. Thanksgiving holiday and days leading up to the holiday. For example, the 1st of Jan was picked as a typical day leading up to a holiday. This is the 3rd of Jan, sorry, this is 2 days after the New Year's, And 1st of August is typically a summer day, which could be expected to be more quiet since kids are still in holidays. But yeah, this graph here is showing how fleet operator is expected to make profit across the different days of the year. And so when we get into fleet performance metrics during the holiday season, like I showed in the previous slide, demand dipped by 42% compared to the regular, working days or regular school days. And we also saw a 30 to 40% drop in profit per SAV. We saw that we also found that EVMT increased on typical work days by 6% from 20.9% to 26.9% on holidays. So on holidays, there was more of inactivity. The fleet wasn't utilized as much during the holidays, which shows from increased EVMT. And the average trip length was highest also on holidays, which showed that there was longer trips happening on holidays, which is what is normally expected, people making longer trips. And peak hour wait time as well. This range between 4.1 to 4.5 was relatively consistent. We have to keep in mind that this was fixed demand across all scenarios, sorry. And then the average VMT ranged from 398 miles on the quieter days or supposed to be typical holiday or summer day, to 528 miles during the work days in the fall. And then we saw 2 to 5% increase in vehicle idle time for the holidays. And also we saw a very low person trips per SAV per day, 27.9% during the holidays. Person trips per SAV per day was highest course, during the work days, it peaked at around 48.2%. And so some key takeaways from this is, so that holidays generally have low demand, longer trips passively, and the lower profits as well on days leading up to the holidays or the work days in the summer, and higher profits on the typical work days in the spring or fall. So higher idle times on holidays, but lower EVMT, higher idling time on holidays and lower EVMT, which could call for various fleet relocation strategies. And then we could factor in factors like market penetration and trip pricing decisions. All these will impact the profit outcomes, and all these weren't included in this analysis. But yes, in any other analysis, if we included all these factors, probably see different behaviors, but mimicking similar results. And so with that ends my presentation, and thanks for listening.
Thank you, Philip. Any question for him? Prakash, do you have a question?
Yeah.
Go ahead.
Yeah. Philip, can you come to the previous slides? That one, the day-to-day variations. Over here. Like you have analyzed for like on a typical means day-to-day variation of a typical holiday with that of either in the summer or the spring or the fall. What is the variation between, because we generally see on the weekend there is a drastic variation between the trips like there is a drastic variation between the trips on the working day and on the weekend. So is it not like that the fall in that number of trips is going to be somewhat similar to on the holiday, somewhat similar to the weekend? Have you analyzed in that perspective? I'm just guessing.
Yes, that's right. So holidays are typically assumed to mimic like weekends as well. So probably didn't mention that, but that's what it is.
Okay, so you mean holiday is comprised of weekend also?
Not really. I mean, the behavior on a holiday is typically assumed to mimic that of a weekend, typical weekend. So it's not like a holiday is also, it's not like a weekend is a part of a holiday. It's just similar travel behaviors on both days.
Any other question from the audience? So I have a question about the Reuters data. Did you have the OD demand directly from the Reuters data, or you had the vehicle counts on links and used an OD estimation to find the OD demand?
So we had the OD directly from the platform. So in the platform, you could just generate OD matrices. Yes.
That is great. Thank you so much, Philip. So we will switch to our next presenter. Our next presenter is Prakash Ranjan. Prakash is currently a PhD student in transportation engineering at the University of Connecticut, working with me, Fatemeh Fakhri Mousavi. His research currently involves the examination of users' parking search behavior and optimization of parking prices at different large-scale urban areas. He's motivated to explore more about users' decision-making process and work more on different traffic simulation tools. Prakash will present his ongoing research on analyzing parking search behavior and location choice using trip trajectory data. Prakash, you can share your screen and start your presentation.
I will just share my screen. Is it visible?
Yes, we can see that.
Yeah. In today's presentation, I am going to present about my ongoing research work on parking search behavior and the location choice using the trip trajectory data. My current research work is being funded by Argonne National Laboratory. Now, coming to our, we know that parking is always an essential component of transportation mobility. It is always difficult to find a empty parking spot in a dense congested area, especially in the bigger cities where parking spaces are limited. Due to which generally the vehicles are forced to go in a cruising, which adds to the already increased number of traffic congestion in our road network. So it becomes very important to model the various factors which influences the driver's choice making process, and we need to incorporate this parking choice model into traffic simulation tools so that we can make our transportation system more efficient, and it will also help us to formulate the policies which will ultimately help us to also cater the dynamic parking demands, which varies a lot during a time of day. Now, a lot of researchers has developed various models like the discrete choice model, the multi-domain models, in which they have tried to analyze various factors which are influencing the driver's decision-making process. And some of them have suggested like we can use the dynamic pricing strategy to mitigate the congestion problems which we are facing. And but like in most of these studies, the researchers have either used the survey data, which means that either revealed preference data or the static preference data or their combination to derive their models. What we are proposing is if we use the trip trajectory data along with that of our survey data, then we will get more insight about the search patterns and the user's decision making process. So our main objective in this, in our current research is first to incorporate the survey data along with the trip trajectory data to have a holistic view of users' decision-making process. Along with after that, we have developed the nested parking choice models in a Bayesian framework. We have used the Bayesian framework over here because the choices available in the survey data are hierarchical in nature, and we know that the Bayesian framework suits best for the hierarchical organized data. And then we have incorporated this model in an agent-based traffic simulation tool to just have know the user preference over broader scale network. Now, coming to the data summary, we have used a lot of data, but our primary source of data was the Chicago metropolitan area, where we have data about the socioeconomic characteristic of the users, land use information, trip informations, and from the survey data, what we found users have many choices to opt from, but we are mainly focusing upon the off-street parking facility, specifically on that garage location and the on-street choices which the user have made. The current survey data represents a sample population around more than 30,000, and the current survey has been done in the spring of 2018 to 2019, in which more than 12,000 of household survey data have been incorporated. And now coming to that data preparation part, what we did because we ultimately aim was to develop a nested logic parking choice model. For that, we needed a comprehensive data set. So first we incorporated all the information available in our CMAP data to in the CMAP data using a unique identifier for all trips among the different data sets. Thereafter, we try to determine the parking location coordinates and destination location coordinates, because these were not directly reported. For that, what we did, we first arranged the GPS point file in the ascending order, and then try to match that arriving time at different different destination with that of a GPS point file, and find out the destination coordinates of those destinations. Thereafter, what we did, we use the backtracking technique, in which we are going in the backward direction till the point the speed is greater than the walking speed, which we consider at 3 miles per hour, and find out the parking location coordinates. And after that, we have filtered out only those trips in which user have used the private vehicles and have either parked at on-street parking facility or at the garage location. Thereafter, we have just matched the destination coordinates with that of available garage coordinates in the Chicago supply file to just know the garage facility at which these the users who have parked at off-street parking facility. We are only, because in this analysis, we are only considered that garage location as an off-street parking location. So we are trying to match the destination coordinates of the users who have parked at off-street parking facility with that of garage location from the garage location coordinates from the Chicago supply file, so that we can ascertain the actual garage number at which the user have parked. Thereafter, we are enriching this data set with that of land use information such as population density and that of employment density by matching it with the EPS smart data using the FIPS code. It was 15 digits FIPS code that was up to a block level. Now, coming to the parking search algorithm, the nested parking choice model which we have developed is later being implemented in a traffic simulation tool, in which the user choice is the user parking choice is planned over here. Like we can say, firstly, the choice model is being called in this framework, the traffic simulation tool framework, and we are trying to determine the user preferences between on-street parking location and the garage location. Say if a user chooses a garage location, then the user's if a user planned for a garage location, then the user simply starts that trip and directly heads toward that garage location and checks the capacity of that garage location. If it is found to be full, then the user looks for the nearest on-street parking locations while it's way to the destination. And if in case the user had planned for an on-street parking location, so then the user directly heads towards destinations, and over there, it checks the capacity of on-street parking location, whether it is there is parking space available over there or not. If it is not available, then an R-tree search run is being initiated to find out the closest available parking location over there. Okay, and now coming to that, I have already discussed the choices made by the user were hierarchical in nature. One was we are considering the on-street, second was the garage. So we have used we have defined the utility functions of the on-street and the garage one as one with the deterministic component, second with the error. And we have used the conditional probability and the marginal probability to determine the probability of choosing any particular garage locations, because the garage location comes in at level 2. First, user choices is distinguished between on-street and off-street facility at the upper level, and then if the user has chosen off-street facility, then the user choice is being you can say categorized into different being categorized to determine the actual garage location where the user have parked. Now coming to the Bayesian statistics as approach, which we have utilized for developing our parking choice model, in which we have utilized the comprehensive data set which we have prepared in the data preparation part to first define the sample size. Then we are initializing beta and lambda. Along with that, we are also initializing the acceptance ratio for the beta and lambda. Thereafter, we are generating 2 random samples based upon using a normal distribution based upon initial beta and an assumed variance. Thereafter, we are determining the log likelihood of the both one, the initial the samples and then the proposed samples. After that, we are determining the prior value for the proposed sample and the initial betas. Thereafter, we are utilizing a metropolis hasting algorithm to estimate the acceptance probability of the proposed parameters. And we are just comparing whether that probability is greater than a random value between 0 to 1. If it is greater than that value, then we are replacing that initial beta and lambda with the new generated beta and lambda. Along with that, we are also updating their acceptance factors. And lastly, we are determining the mean and a standard deviation of the beta and procedural distribution, along with that acceptance rate of beta and lambda. And finally, we are reporting that mean and variance of beta and lambda along with their confidence intervals. So what in this Bayesian statistics approach, we have used around 10,000 of many iterations, and along with that, we have used Gaussian distribution for the hyperparameters and since prior for the inclusive values. Now coming to that model assumptions, we have assumed a lot of assumptions. The first was like we are treating all the on-street parking location as a single unit. That's why we have defined a random number between 0 to 0.3 kilometer as a distance between the destination location and the parking locations. And thereafter, we have also limited the parking search for a vehicle. Parking search for a vehicle within a radius of 5 kilometer to the radius of 5 kilometer from the destinations, and we have also limited we have kept the higher price of the garage to a $20 per hour. Apart from that, we have also incorporated trip importance as an attribute to our parking choice models, in which we have only incorporated the choices of the users who have indicated that there is the importance of arriving on time on their destination was either very important for them or like extremely important for them. Now coming to our parking choice model, like we have in the parking choice, we have tried to determine the various factors which are influencing the user's decision-making process. Like the first one, like here distance represents the distance between the destination location and the parking location. So from the negative sign of the beta coefficient, it clearly indicates us that as the distance between destination and parking location increases, there is very less chances of user preference towards that parking location. Similarly, the case for the parking fees. As we go on increasing the parking fee for a particular parking location, the user are less likely to select that parking locations. Now, the timing of the trip also influences the user's choice about particular parking locations. Particular parking location. If the generally it is found like the trip which is done during the peak hours, that users generally prefer to park at the garage location just to save the times which might be lost during in finding the available on-street parking options, and during peak hour generally users didn't have that much time because they have to report early at their work or at their office. Apart from that, we have also tried to analyze the land use attributes such as the population density and the job density, for which the beta coefficient over here clearly indicates us that, like, if in an area there is very high population density or the job density, then the users over there is more likely to go directly to the garage option because they knew that there will be very less chances to have a available on-street parking location. Also, it will save us the times and like you can say the time and the effort in finding parking locations. Apart from that, like in our next step, what we have planned to do is like we already knew that our nested parking choice model we have implemented in agent-based traffic simulation tools. In that, what we are doing, like in the first step, we are increasing the parking prices of different parking locations, keeping the parking capacity the same. So we are trying to analyze if we are going to increase only the parking prices, what is the variation in the user's behavior after increasing the prices, whether they are going to park inside, whether more vehicles are parked on street or like on off street, whether there are more vehicles are inclined to park within the CBD zone area or outside the CBD zone area. So we are trying to observe those variations in the in next few scenarios. We are keeping the capacity as the same and then trying to reduce that capacity. First trying to reduce the overall capacity, and then only trying to reduce the on-street capacity and allocating it to the freight ones, because we also have a lot of freight vehicles over there. And then we are trying to analyze the parking choices of the users, how that is going to vary. Apart from that, the same scenario we have done like in the lower part, like instead of increasing overall prices of off-street parking, instead of increasing only the off-street parking prices, we are now increasing that off-street parking prices only in the that you can say CBD zone area, and keeping the capacity same. So the main purpose of all this scenario is to analyze the user choices made by varying the different attributes, how they are sensitive to these changes. And lastly, currently, like our analysis for the scenario is currently in the progress. And if you are interested in our research work, or like if you want to know the final result of those analysis, you can definitely contact us. And if you have any question, I am ready to answer this. Thank you.
Thank you, Prakash. Any question for Prakash? No questions? Okay. So with that, we will go to the third presenter. Our third presenter is Mostafa Abolfazli. Mostafa is pursuing his master's degree in industrial engineering at Polytechnic University of Montreal in Canada. His presentation is related to the research that he has done during his first master's at American University of Technology in Iran. His research interests are public transport planning, travel behavior analysis, and the application of machine learning methods in transportation systems. Mostafa, the floor is yours. You can share your screen and start your presentation.
Thank you for introducing me. Hello, everyone. Thank you for joining me today. Let me first share my PowerPoint. Okay. So, can you see my slides now?
Yes, we can see.
Okay. My name is Mostafa Abolfazli. Today I'm going to share with you the results on the previous research that I've done at American University of Technology. The topic I'm going to present is detecting and characterizing individual versus group travel behavior in public transportation. And before we begin, I'd like to acknowledge the contributions of my co-authors, Dr. Mahmoud Mesbah and Dr. Ahmed Reza Ghaffari. So public transportation passengers account for a wide range of people in the society who might demonstrate different types of travel behavior. And travel behavior refers to the decision-making process of travelers for their trips, including time of travel, destination choice, frequency, and travel distance. In recent decades, with the emergence of automated fare collection systems, a detailed record of travel data is available, which by analyzing this kind of data, different travel patterns can be revealed both temporally and spatially. So public transport agencies can use this kind of information to better meet passengers' demand and improve the functionality of the system. In the literature, travel behavior has been categorized based on different aspects. For example, travel behavior analysis of different socioeconomic groups, travel behavior analysis of different types of travel modes. And also, we can analyze travel behavior individually and travels as groups. So in this paper, group travel behavior refers to the studying of a passenger's behavior when accompanied by at least another passenger. So why we need to study group travel behavior? Because it helps us to design a more optimal service schedule to adjust the frequency of the service. And it can help the public transport agencies towards the development of a group ticketing policy. For example, discounts on group tickets to attract more passengers to the system. Although individual travel behavior is a well-studied topic in the literature, limited work has been done for analyzing group behavior. And most of the previous works mainly aimed at the classing passengers based on their trip features, the time of travel, the location they travel, etc. there were a few research gaps that led us towards this study. First, a lack of a comparative analysis of individual travel behavior and group travel behavior in a bus system. Second, a lack of an efficient algorithm for detecting group trips. And also, previous studies had limited extent of study period, or they considered limited characteristics of travel behavior. So we had few objectives in this research. Firstly, OD estimation of a bus system trips using smart card data. Second, classifying trips as individual or group trips. And finally, comparing individual with group travel behavior, considering different aspects of trips, including temporal pattern, spatial pattern, travel frequency, and travel distance. So we chose Arak city bus system as our case study. Arak is an industrial city in central Iran with a population around 500,000 people. Public transportation of this city uses a tap-out flat fare AFC system. It means that each passenger tap his or her card when alighting a bus, and the data includes card ID, date and time of alighting, bus ID, fare amount, and the balance of a smart card. We used 10 months of smart card data in 2015 and 2016. And overall, more than 4,300,000 transactions were made during that time by more than 64,000 unique cards. Here you can see in these charts the hourly distribution of transactions by days of the week. It is noticeable that the temporal patterns for Saturday to Wednesdays are very similar, where a morning peak is around 7, a noon peak around 12, and there's an evening peak at 16 o'clock. I should mention that in Iran, the working days start from Saturday and ends on Wednesday in most cities, and Thursday and Fridays are weekend days in Iran. So on these days, most of the companies and the schools are closed, so less trips are made by people by public transportation. So we developed a multi-stage methodological framework for this study. Our main challenge was that we neither the alighting location nor boarding location was registered in the smart card data. So at the first step, we needed to estimate the alighting location of a smart card transaction based on AVL data. Then at the next step, we estimated the boarding location based on classic trip chaining method and also clustering method that we used combined with trip chaining method. And in the last step, we identified individual and group trips and compared them based on different features of the trip. So I'm gonna explain each step in more detail. At first step, we use AVL data to estimate alighting location of smart card transactions. So in AVL data, the bus ID, arrival time at each stop, and the stop ID were recorded. And in the bus system of Arak, each bus starts from a terminal station and returns to the same station at the end of its route. So they move in a tour on the network. So we can calculate tour time of each bus line based on the AVL data. And then we defined an equation here to calculate the percentage of the tour time for bus to reach a station. In this equation, PI is the percentage of the tour time taken for bus to reach a station I, and TI is the part of the tour time that takes for the bus to reach the station I, and T is the total tour time. So then based on this tour time and the percentage of the different stops, we separated tours in the smart card data. And because the percentage of the consecutive stops were very close, we decided to estimate the alighting zone of each transactions. In next step, we estimated boarding location of transactions. One of the main assumptions of the trip chaining method is the existence of at least 2 trips per day for each passenger. But what if only one transaction in one day is recorded for smart card data? So we came up with the idea to cluster the transactions of each smart card data over a time period. In this study, 1 month, to determine where each passenger made most of his or her trips. And the input of our clustering algorithm was the time and location of alighting. And we considered 2 clusters for each smart card data. And cluster centers here basically represents the probable home and work or education place for each card user. And in the final stage, when we estimated the OED metrics for all the trips, we used the proxemic theory to identify group trips. And according to proxemic theory, persons engaged in group trips can be assumed to keep a small distance between each other during a trip. So we use the time interval between transactions as the indicator of group trips. And in our case, group trips can occur in 2 ways. Group trips taking place by using a single card, and group trips that take place using different cards. So in Iraq, a single card can be used multiple times. For example, someone can tap his card for his friend or for someone that accompanies him. And since we have the balance of each card in the transaction data, we can see that if these multiple transactions were made intentionally or not, or it was an error of the system. So we considered the time gap of less than 10 seconds for the detection of group trips. And here if the time difference between 2 consecutive transactions were less than group time lag, those 2 transactions are group trips. And if the time difference is more than 10 seconds, those transactions were labeled as individual trips. So here, this plot shows the percentage of individual trips and group trips during days of the week. It can be seen from this figure that the percentage of individual and group trips are almost the same on working days. While on weekends, the percentage of group trips increases. On weekends, especially on Friday, due to the closure of schools and companies, business trips, which are usually done individually, decrease, and leisure trip, which are more likely to be done in a group, increased. So out of the total of the trips, 66% were labeled as individual trips and 28% as the group trips. So in this slide, you can see the temporal patterns of individual trips and group trips on weekdays. Left figure represents the temporal patterns of trips over the hours of weekdays. On these days, for both individual and group trips, 3 peak hours were recorded in the morning, noon, and in the evening, which is aligned with the opening hour of offices and schools. Also, the maximum number of group trips has occurred between 6 to 7 p.m. And on the right figure, the percentage of individual and group trips per hour of weekdays is displayed. It is observed that, in the early hours of the morning, from 6 to 8, less than 20% of the trips were made in groups, while during the evening hours, from 6 to 9 p.m., the percentage of group trips has reached 35% of the total trips. Here you can see the temporal patterns of trips on weekends. On the left figure, unlike the weekends, there is no morning peak hour. And due to the closure of the companies and educational centers on these days, fewer trips have been made in the early morning hours. And you can see that on the right figure, the percentage of the individual trips and group trips were shown, and about 85% of the trips in the early morning hours of the day were made individually, and 50% in the early morning hours of the day, and less than 50% of the trips were made in groups. By approaching the midday hours, the percentage of group trips increased. To compare the spatial patterns of individual and group trips, the distance of the travel destination from the CBD zone has been used, and the direct distance of the alighting zone of each trip from the CBD zone was calculated on the network. And we defined 6 levels of distance, trips with the distance of less than 1 kilometer to CBD, till the last level, which are the trips with the distance more than 5 kilometers to CBD zone. And here you can see that the percentage of individual and group trips of each level on the weekends and weekdays. It is observed that on weekdays, around 60% of both individual and group trips were at level 1 and 2. It means that most of the trips on these days have been made in areas with less than 2 kilometers from the CBD zone. So since the focus of Iraq City jobs, companies and organizations is in the CBD zone, the attraction of group of work trips to the central areas of the city is more. So, which has led to the considerable share of individual trips on these days. And we observed the same results on weekends, and because the focus, there's recreational centers and entertainment centers in the CBD, so the more group trips were attracted to the areas that has the distance of that were close to the CBD zone. We also compared compared individual trips and group trips in terms of travel distance. The distance between the origin and destination of each trip on the public transportation network model was considered as travel distance, and the number of trips made between each pair of OD was taken from the OD matrix. As you can see in this chart, the focus of the data is on the left side of the graph, which means lower distances, and the frequency of individual and group trips decreases as the travel distance increases. Group trips were more concentrated in relatively lower distances than individual trips, and individual trips had higher frequency percentage than group trips on longer distances. And lastly, we compared individual and group trips based on travel frequency. We consider the average number of trips per week. It means that the total number of individual trips and group trips of each smart car was divided by the number of weeks it has been used. And here you can see, based on this figure, the frequency percentage of group travel is decreased with increasing travel frequency, while the frequency percentage of individual travelers increases with increasing travel frequency. So it can be inferred that individual trips had more repeatability than group trips, and most of the passengers that made group trips, they made this kind of group just once a week. So in this study, we compared individual travel behavior and group travel behavior of passengers using bus smart card data in Iraq, Iran. A method for estimating transactions alighting zone was presented based on AVL data. The trip chaining method and k-means clustering algorithm were used jointly to estimate the origin and destination of trips. Our findings revealed that 28% of passengers experienced group trips during the study period, with group trips occurring more on weekends and in the afternoons. Regarding spatial patterns, no significant difference was observed between individual and group trips. And individual trips had more repeatability throughout the week compared to group trips. And our proposed approach can be used in any public transportation network with a similar AFC system. Although some limitation exists, our approach might incorrectly identify some individual trips as group ones. And for the future works, considering other metrics such as trip coexistence among passengers over an extended period might enhance the results. Thank you for your attention. Feel free to share any questions or comments you might have.
Thank you, Mostafa, for your presentation. We have time for only one short question. Any questions from Mostafa? Prakash, go ahead.
Yeah. I just want to ask, like you have mentioned that like you are considering two trips as a group trips only when there is a time difference of 10 seconds. But say what would we say, like when there is a very rush over any particular bus station, like people are rushing to go inside the bus station, there might be like might be individuals one, but the timing between those like swapping the card might be lesser than the 10 seconds. So how you are distinguished between that individual one and that of the group trips?
Yeah, that's exactly one of our main limitations of this study, because we consider the time gap between the transactions that had the same alighting and boarding location. So we didn't consider any more conditions to detect group trips. But I should mention that most of the group trips that we detected were based on just a single smart card, because a single smart card can be used multiple times, and each time it's used, the balance of the card decreased. So we can say that there were some people that were traveling together and they used just one card. But for the trips that were made by different cards, yeah, as you said, that's the challenge for detection. Yeah.
Thank you.
Okay, great. Thank you so much, Mostafa, for your great presentation. Our next presenter is Osama Mohammed. Osama is a senior traffic and transportation engineer with more than 20 years of experience in design and management of complex transportation systems. Osama has been a project manager for different projects for Missouri Department of Transportation, Illinois Department of Transportation, Illinois Tollway, and different municipalities. He will present his research on short-term incident prediction today. Osama, please go ahead and share your screen.
Can you see my screen? Great. Thank you for the good afternoon and welcome everyone to my paper presentation titled Short-Term Incident Prediction, a Binary Relevance and Label Power Set Approach. This is a summary for what will be covered in today's presentation. I will start with my research contribution and objective. Proactive traffic management will be discussed after. Then I will talk about the literature. I will spend some time to discuss the methodology and the proposed framework. Next, the case study will be described. The findings from this paper will be summarized. And finally, conclusion will be provided with suggestion for the future research. So the current body of research does not distinguish the type of crashes that can be expected on roadway. This paper is the first to predict the crash type that can be expected on the roadway. This knowledge will assist transportation agencies and first responders to prioritize the incident that will require more resource or may have higher impact on the network. This paper aimed to improve the spatial resolution predicted crashes and offer crash prediction on freeway section. This will help the first responder to minimize their overall expected response time and take preventive action. Finally, and according to our knowledge, crash prediction on the basis of multi-class and multi-label is investigated for the first time in this paper. This approach will help to predict the number and type of crashes that can be expected on each predefined section on different freeway segments. So why do we need for proactive traffic management? Around the world, traffic incident is the main source of non-recurring congestion on a freeway, which cause delay, air pollution, injuries, and fatalities. The objective of the proactive traffic management is to allow transportation agencies to adopt strategies such as mitigate congestion, prevent crashes, and improve the safety, reduce the impact of roadway crashes, adjust traffic control system such as RAM metering and variable speed limit, reduce speed pollution, which result in improved quality of life in urban and rural areas. And the last but not least, the proactive traffic management can help provide active freight and transit management system as well. An intensive literature review was conducted to review the state of art in crash prediction and to determine the knowledge gaps and shortcomings of existing methods. This table showing the most researchers that were conducted in area of crash prediction. Attention was given to some important factors, including the study area length, the sample size, predictor variables, and model accuracy. Looking to these researchers, gap in each type in crash type prediction was noted. Gap in identifying number of crashes per section was also observed. This slide also shows more research that were conducted and reviewed for the area of crash prediction. So in order to reach our goal, we had to develop a study framework. This paper proposed a framework to develop models that predict location and type of crashes on a predefined section of roadway system within 1 hour interval, historical traffic data including the speed, traffic flow, and occupancy with the crash logs for several freeway sections were used in this paper. First, geographic information system is used to predefine roadway section for each segment. Second, a quality control test using the open source R software are conducted to identify unreliable data. Finally, computer scripts were developed to merge the crash data with roadway traffic stream parameters. The final merge database are pre-processed using two transformation approaches, namely binary relevance approach and label power set to convert the dataset into a format that can be modeled by classification methods. Once the data set being pre-processed, the database were split into two parts. The first part was used to train the model with best selected hyperparameter. The second unseen part of the data set was used to evaluate the developed model. A multi-class, multi-label sampling learning-based classification model using random forest and a greeting hosting machine were developed using the transformed database to predict the number and type of crashes that are expected to occur on a section of a freeway system. The last part of the study framework include the crash prediction results and the performance measures that are used to evaluate the results for the crash prediction model. Accuracy, recall, precision, and F1 score and false positive rate are used to evaluate the results. In the literature, classification models are commonly developed to predict one response variable. This is considered a single label and binary class model. The model is a single label because it's only considered one roadway segment, and considered binary class because, for example, it can only predict whether a minor crash will occur or not. A multi-class classification model can predict if a minor crash, a crash, or multi-vehicle crash, or no crash will occur on the roadway segment. This figure here shows that multi-class, multi-label can predict several types of crashes within a roadway segment. Unlike the two previous classification models, this figure shows a multi-class model that can predict more than one label target at once. This type of model will be able to provide crash prediction for more than one section within one model. A multi-class, multi-label model will consider the specific pattern on more than one roadway section and can predict the number and type of crashes that are expected to occur on section of the freeway system. So the question here, why we need transformation approach? And the answer for this question is first, to pre-process multi-class, multi-label database or dataset into a single label data set. Second, to untackle the multi-class, multi-label problem so that it can be adequately modeled by a common classification algorithm. And with this process, a crash prediction model that can predict the type and the location of crashes on several sections of roadway can be developed. So in this paper, label power set and as previously mentioned, label power set and binary approach, binary relevance transformation approach are used to pre-process the traffic and the crash data for a predefined section on a freeway network. In label power set method, the multi-label multi-class problem is transformed to a single label multi-class classification problem. While in the binary level transformation approach, a multi-label classification problem is decomposed to several distinct single label binary classification problems, and this will help to predict type of location and to predict type of crashes and number of crashes on different sections. The random forest method is a combination, one of the methods that technique used to develop the prediction model. It's a combination of decision trees where each tree is trained using a randomly selected subset of training data. In this method, each tree of the forest predicts a class for each instant. The class that is predicted by most trees is voted as the final class. An gradient posting machine, GPM, is an assembly learning method where a leaf learner is gradually modified to improve the accuracy of a regression or classification model. The GPM works based on three main elements. These elements included loss function, weak learner, and adaptive model that used to minimize the loss function. To help understand the result obtained from prediction machine learning models such as random forest and gradient posting machine, a variable importance evaluation method is adopted in this paper called random forest variable importance method. A higher score indicates that a variable has more substantial role in obtaining accurate predictions. Accuracy, recall, precision, F1 score, and false alarm rate were used to evaluate the developed model. These performance measures are calculated on the basis of four main elements. These elements include T crash, which is true crash, true non-crash, false crash, false non-crash. Crash prediction model were developed for a portion of the Interstate 270 network in St. Louis, Missouri, United States. 5 sections were selected on the basis of availability of archived traffic data, historical incident log, and roadway geometry data. The freeway segment was further divided to a smaller section to improve the spatial resolution of the crash prediction model. This segment includes 6.42 miles of Interstate 270. Roadway geometric data were obtained from the Missouri Department of Transportation data zone. Number of lane width, and shoulder width geometric data were also used as a predictor variable. Incident log were recorded by Gateway Guide Traffic Management Center in Missouri Department of Transportation. Crash were categorized as a minor crash, a multi-vehicle crash, and these data were distributed on each section of the entire segment. This section discussed the main findings of this paper. So 4 categories of model were developed in this paper to predict the number and location of the crashes of I-270 during 1 hour prediction interval. In general, random forest model performed better than the GPM model in both transformation approach. However, when we're choosing a transformation approach for the random forest model, trade-off should be considered. Performance measure obtained from the label power set transformation approach were slightly more desirable than performance measure obtained from binary relevance transformation approach. This potential is due to the fact that the power set transformation predicts the location of crashes and cannot predict a crash type. And in contrast, the binary relevance transformation approach predicts both location and type of crashes, which in turn increase the complexity of the model. Considering the small differences between performance measure for both approaches and the benefit of knowing the expected incident types, the random forest model developed on the basis of the binary relevance transformation approach is the preferred method for spatial and temporal incident prediction. This table reports precision, recall, F1 score for all 5 sections from A to E of Interstate 270 for 4 scenarios at each section. The higher value for the precision, recall, and F1 score are more desirable. Generally, the model performs well when there are no crashes to be expected on the roadway. The precision value for the 5 roadway sections are also near perfect. However, recall F1 score for section A and E are less than ideal. So in this figure, we're showing the binary relevance random forest model confusion matrix for section A to E. This confusion matrix is based on numerical code from 0 indicate that no incident occurred on the roadway section, and then the 3 is mean that there is a multi-crash occur on the section. A perfect model will result in so the perfect model usually should be result in diagonal confusion matrix. That means that the model 100% or correctly predict the crashes on the section. However, it is not always possible to develop a perfect model specifically for a problem as a complex as short-term crash prediction. As we mentioned, this figure also shows the predictor variable importance for binary relevance random forest model. The results for the variable importance indicate that the occupancy at section A, occupancy at section C, and the occupancy at section E are the top three most important variables for the crash prediction. This is a constant with the traffic flow theory, where density or occupancy is considered the primary traffic flow parameter that corresponds with quality of service. So, as a summary and conclusion for this research, the model proposed in this paper predicts location and type of crashes on the basis of observed traffic pattern on a roadway segment. Approaches developed on this paper applied on the 5 section of Interstate 270 in St. Louis, Missouri. Multi-class, multi-label classification method were used to develop the crash prediction model. The binary relevance and label bar set are the two performance transformation approach were used with random forest and the gradient ultimate machine technique algorithm. A random forest model outperformed the GPM model, and the result obtained from binary relevance transformation approach and label power set were compatible. And random forest model developed on basis of binary relevance transformation approach was considered the best, since it can predict both incident type and incident location. The crash scenarios that are frequently occur are more likely to show desirable performance. And finally, the occupancy is found to be the greatest contributor on predicting of crashes, while volume generate the second greatest impact on predicting of crashes. For future research, investigate additional data can improve the model accuracy, extend time span of historical training data using larger database may enable application of deep neural network for prediction of crashes, and finally, developing a hyper flow crash prediction model that take into account the motor impact of the crashes on the flow, and the flow on the crashes may improve the accuracy of both crashes and the flow prediction. Thank you for attending, and happy to answer your question.
Thank you so much, Osama. Dr. Koppelman had a question, so do you want to ask it yourself, Dr. Koppelman?
Yeah, Osama, can you share your video? Prakash, you don't need to do that anymore, but yeah, it's we'd love to see our speakers.
Prakash.
Oh, Prakash doesn't have a headshot in the background. I could see why he's sharing his video. Osama, are you here in the US right now?
Can you say it again?
Oh, can you share your face, your video?
Oh yeah, okay.
You guys are so shy. Anyhow, Prakash, we love seeing you. You're welcome to redo that again. I thought you had a headshot in the background like Mostafa and some of us. It's really easy to change that. Hey, Osama, great to see you. Get to see a little bit of this house there. This is my office.
Opening a few different monitors. Maybe that one that's giving me the camera, that's why.
Well, don't worry, I'm not going to ask you about the slides, but I am interested in the use of the word incident, because it's really hard, and I've just been waiting for more researchers to see if they can find other incidents, because those disrupt traffic, sometimes worse than a crash, like a mattress or a dead animal or something in one of the lanes. And they can slow traffic quite a bit. So do you have any thoughts on introducing that kind of data?
For the incident?
Yeah.
Reviewing the different literature review, like the focus was on how to see if there is a crash will occur or not. So different factor so the main goal of this paper or research is to allocate where more crashes will occur on some sections, then then the next step is to see what's the reason of these crashes. It could be like, that's why we include different type of parameters, like for example, geometric parameter, speed, traffic data parameter, crash data. So if we, the next step is when we check like this section, it may have more crashes occur, then we go back and see what is the main factor that reflect or affect this number of crashes. So if it's geometric, then we go back and we see, is there an issue with the like curves, horizontal curve, vertical curves, and then we start doing some treatment based on what factor has more contribute to the crashes. So it's different from case to case. It's based on what's the main factor. So if, as we can see here, occupancy, volume, or speed sometimes give some other models, like taking into consideration also some factors like texting or using a phone. These also another factor that increase the number of incidents or crashes on freeway. So based on what we found, we can go back and do more analysis to see and improve and prevent actually or reduce the number of crashes.
But yeah, crash frequency prediction as a function of geometric attributes is a long-studied subject. So I'm really hoping somebody's going to get into other types of incidents. I think Chicago has some good data from their 911 and their 311 phone calls. And of course, China has cameras everywhere. So this morning, actually it wasn't this morning, I guess it was last night for most of us, the Eastern sessions kicked off in the Eastern Hemisphere. And one of the first presenters was the guy at Tsinghua University, which is China's #1 technical university, I believe. And it was excellent. It was about reinforcement learning to try to replicate the crash, actual crashes based on the trajectories that drivers tend to follow as they try to avoid each other to not hit. So lots of near crash events and that kind of thing. And so he was looking at different types of geometric sessions, but you may want to look his up. I think his first name is Shu or Shou, SHOU, something like that. And he's in the program along with the rest of you speakers and co-authors. So anyhow, I just thought I'd put that plug in for other incidents reporting in case any of you is looking for a new topic to tackle.
Thank you. And just one more thing to add is the weather, also one of the factors that we are working on on another paper, that it has really main contribution to the crashes, like to reduce or increase number of crashes as well.
Yeah, I'd love to see more about weather too, and that's much easier data to grab. So to pair it with some of these traffic flow stuff, yeah, it is very interesting.
Hey, great. That was a great discussion. Thank you so much for the presentation, Osama.
Sure.
Our next presenter is Shijie Chen. Shijie is a PhD candidate in industrial engineering at Florida State University. His studies focus on mathematical modeling of transportation systems to optimize, analyze, and control mobility services. Shijie, floor is yours.
Yes, thanks for your introduction. Osama, could you please shut down your screen sharing?
Osama?
Oh, thank you.
Thank you.
So, hi everyone. What I'm going to present today is a project that I worked with my advisor, Dr. Sun. This project is to develop an optimization model for the schedule negotiation with riders in ADA Paratransit. The ADA requires our government to provide an equally accessible transportation service. That service is to serve for those disabled people. And this kind of service is also called direct ride service. This is a door-to-door, shared ride, and on-demand service. ADA also permits a schedule duration of less than 1 hour. The schedule duration could enable a higher service efficiency. For example, we can show in this figure. If we look at left-hand side, now we have 3 different riders. they are from different pickup location, but they have the same destination. Even though they have the same destination, they have the same requested pickup time. So the operator may have to dispatch 3 different vehicles to serve individually. But because of the limitation of the fleet size, one customer may not be able to be served. So in case the operator can smooth the trip request using the schedule deviation, then the rider's pickup time can be shifted and one vehicle may be sufficient to serve all the 3 riders to deliver all of them to the same destination. In that case, all customer can be served as well. So we can see with the schedule deviation, the higher service efficiency can be achieved. Practically, the schedule deviation is a kind of flexibility. According to the literature review, the flexibility in Paratransit have been studied from multiple perspectives, such as the transportation modes, destinations, pickup location, service time, and pickup time. I want to highlight the last study because it's the only one that consider the customer behavior using a utility function. But they did not consider the behavior uncertainty of the customer because those utility functions require the privately unknown information of riders. Those information are unknown and could be uncertain. That uncertainty should be captured by our model as well. And from another perspective, the customer behavior is typically studied in the demand management area, especially for the attended home delivery problem. Even though there have been extensive study for studying the demand management in those areas, those models cannot be readily transferable to ADA Paratransit because ADA literature HD literature generally does not address the routing optimization problem. Instead, they usually only approximate the routing cost to focus on the customer choice modeling only. So this is one of the research gap. So we combine both of them, we can conclude that there's a research gap, that there's no studies to consider the schedule negotiation by realistically modeling the choice behavior, especially the uncertainty of the Paratransit rider with private information. So we are going to handle this research gap, and the problem can be stated in this way. We want to address a dynamic routing problem, and we hope that we can negotiate the schedule with customer. The operator can provide incentive for the negotiation. The customer can look at the incentive and compare the estimated value of time with their true value of time. In case the provided value of time is higher than the true value, then the customer will accept that scheduling. Otherwise, will reject. The value of time will be calculated in this way. It will be incentive divided by the schedule deviation. So we are going to do the trade-off. We want to minimize the incentive. This is part of the total cost. And we also want to maximize the acceptance probability. In case our deviation is accepted, we can enjoy the higher flexibility. So we hope to increase the acceptance probability. That is to increase the value of time. This is kind of trade-off. And we have another assumption that the value of time of all customers will follow the same normal distribution. And then this figure illustrates the process of booking, arrival, and confirmation. Remember that we are focusing on dynamic routing problem. So now we are service provider whenever any new arrival of a new booking arrive. And then we have some existing route. We are going to insert this new rider to those existing route by solving one optimization problem that has an objective to maximize the incremental payoff by considering so many decisions such as the routing, scheduling decision, and deviation, and incentive. I want to highlight that in this incentive decision, we are actually optimizing the estimated value of time. There's this one. We want to provide a higher estimated value of time, give this value to the rider, so the customer will compare this estimated value of time to the true value of time. In case we provide a higher value, that rider will accept our proposal, our deviation proposal. Otherwise, we reject. According to the feedback returned to our service provider, the service provider will make the booking confirmation accordingly and update the route accordingly. And this slide will show all the notation we used for formulating our problem. We call that problem as a booking confirmation problem. This is a formulation. We are going to maximize the incremental payoff for one route, omega, because we are going to insert one new rider to some routes. For each route, we are going to solve one such a problem. In this problem, we are going to optimize the insertion decision, scheduling decision. We respect the maximum wait time and time window constraint. They are all standard. And more importantly, we are going to optimize the deviated time window, denoted as the B. B represent the magnitude of the deviation. So we can know what kind of deviation we can use. And the B value, the deviation value is limited by upper bound. That is the maximum deviation. So when we have this problem, we call it BCP. When we have this problem, we can consider two scenarios. In case we limit the upper bound at 0, we actually do not allow any deviation. We can have a backup plan. That means in case the customer reject our plan, our with deviation, we can still have a backup plan. We call the plan as plan 0. We do not allow any deviation. And at the same time, we can solve this problem again with a positive maximum deviation. In that case, we are allowed to have deviation. We have another objective value. We have another solution. That solution is called plan 1. Deviation is allowed it, and we have hopefully we can have a greater incremental payoff value, the objective value. We call that value as delta pi 1 omega. So I want to record our problem. Our problem is that we hope our customer, our one new customer, accept this plan 1 as long as we provide sufficiently great estimated value of time. As long as our estimated value is greater than the true value of time, the customer will accept this plan. But in case our plan is rejected, we still be able to insert that customer to the existing route with the backup plan. We still be able to enjoy this delta pi 0 omega, sorry. And so, but we cannot provide too much incentive because incentive is also part of the cost. So we are doing the trade-off. We want to know how much incentive should we provide to ensure a sufficiently high acceptance probability and lower operating cost in the plan 1. This kind of trade-off is done in this problem. This problem is called negotiable booking confirmation problem. This phi function is the CDF cumulative density function of the normal distribution. V is our optimized value of time. Mu is the parameters that representing the mean value of the normal distribution. Sigma is the standard deviation. So this is the acceptance probability. Delta pi 1 omega is the variable representing the incremental payoff in case our good plan is accepted. So 1 minus acceptance probability would be the rejection probability. In case our plan 1 is rejected, we still have plan 0. This is a constant. When we have no deviation, our plan would be fixed. With this objective as the delta pi 0 omega. So we are going to solve this problem. At the same time, we respect all the previously mentioned constraints. And practically, this problem is a non-convex mixed integer nonlinear program. So we should not use any commercial solver to solve this problem. We developed some one solution approach to solve that problem, but because of the limitation of the presentation time, I'm not going to cover that part in my presentation. So we next move to the case study. We developed some instance to test our effectiveness of the schedule negotiation. We define one instance as the one booking confirmation for one new rider and some existing routes. And then we generate 42 instances. This figure represents the results of one of the results. Each point represents one instance. So there are totally 42 points here. The x-axis means that how much incentive we provided. We can call it investment. And the y-axis represents the incremental payoff, or we can call it benefit obtained. And then with so many points, we can calculate average revenue on investment. So and then we can get the average ROI as 4.1. That means averagely, when we provide $1 of the incentive, we hopefully can obtain around $4 of the return. So these results demonstrate the effectiveness of our schedule negotiation. And next, we move to the experiments on real-world instance. We have the real-world dataset from Challenger Transportation. We totally have 377 riders, and we set 20 of them as the subscription trips. Subscription trips means that we know them in advance at the beginning as a dynamic problem, so that we can solve some routing problem for them. We can get the existing route for all those subscription trips. And then all the remaining 217 riders would be regarded as individual instance. So we totally have 217 instances. And then let's see, this is the spatial distribution of the pickup and drop-off location. This table represents the parameters we used for our real-world instance. And then the first experiment we conducted for the real-world instance is that we want to benchmark with a simplified negotiation policy. Recall that in our proposed policy, we optimize several problems, especially for the estimated value of time. We want to optimize the value estimated value of time. We want to increase that value to ensure higher acceptance probability, but we do not want to provide too much incentive because they are part of the cost. So we are doing the trade-off here. In case we simplify this process by provide a constant value of the estimated value of time, that means we provide a standard compensation rate as the same as the mean value of the value of time. In that case, we want to see how would our models perform, how would the performance difference. And then we can see that in our proposed policy, we tend to provide slightly higher estimated value of time. And because we are providing a higher compensation rate, the compensation is too expensive. So we tend to use a smaller deviation. So together we tend to have a slightly greater incentive provided to the customer. And because we are using a greater compensation rate, we can ensure a significantly greater acceptance probability. And then eventually we can guarantee a much higher expected return, so that we can see that it's necessary to optimize the estimated value of time instead of using a constant value. And then next, we conducted a sensitivity analysis on mean value. Mean value is the mean value of the value of time distribution. That means in different service area, we may have different kind of customers. Some markets may have a distribution with higher mean value of time. In that case, we want to see how will our mechanism behave. And then we can see that with a higher value of mean value, we tend to provide a higher estimated value of time, and our deviation would be smaller, and our incentive will increase as well. Our expected return would decrease, our expected payoff would decrease. But I want to highlight that there's a breakpoint here at around mu equal to 5. I want to interpret these results. When we have a market, those customer in this market tend to have a smaller value of time. They usually have a smaller mean value. In that case, we can provide smaller estimated value of time to them. The compensation rate is cheap, so we can provide a greater deviation. Even though we provide a great deviation, we are still beneficial to negotiate with them. Otherwise, in case in a market with a very expensive compensation rate, we have to provide much more estimated value of time. In that case, the compensation is too expensive. We need to reduce our deviation. That results can be presented here. I'm going to show two figures. One is for the updated route with smaller mean value. Another one is with greater mean value. So in this figure, this node represents the pickup time. This is the drop-off time. This is its original schedule. This is deviated schedule. In this figure, we represent the updated route when we have a small mean value. because the compensation is too cheap, so we can enjoy the great deviation, we can still get benefit from the negotiation. Otherwise, in case the compensation rate is too high, we have to reduce our deviation. Otherwise, we will get less benefit, get a higher cost because of the increased incentive. So this is why when we have a higher mean value, there's a breakpoint and we tend to use a smaller deviation. And next, we conducted a sensitivity analysis of the sigma. Sigma captured the uncertainty of customer behavior. We can observe the similar trends of so many metrics over the change of sigma. When the uncertainty increase, estimated value of time will increase, deviation decrease, real breakpoint here. The incentive will increase as well, even though there's a breakpoint here. The expected return and the expected payoff would decrease with the change of sigma. All those results are focusing on only one negotiation instant. But we also want to look at the results on multiple instants because we have totally 217 instances. So this is a sensitivity analysis of the maximum deviation. All those results are mean value of the results that conducted on a totally 217 instances. When we have a greater upper bound, we are practically relaxing the problem. So when a greater deviation is allowed, the model tends to use the greater deviation, but the estimated value of time does not change. So together, eventually the provided incentive would slightly increase and the acceptance probability does not change. And finally, the expected return would increase as well. So this figure gives us the insight that if the policymaker can allow the greater maximum deviation, that will be great for our operation performance. But the policymaker may also need to respect the customer satisfaction. So finally, we can draw the conclusion, and we developed a negotiation mechanism that would consider the flexibility in Paratransit service and the distinct value of time of customer. Because this problem is non-convex, so we developed a two-tier decomposition technique to solve the problem. According to our experiments on synthetic data and real data set, we identified the effectiveness of our mechanism, and we found that it's necessary to optimize the estimated value of time with our negotiable booking confirmation problem. We also quantified the effect of the schedule deviation on the performance metrics. So thank you for your listening. Welcome to your question.
Thank you so much, Shijie. Is there any question? We can have one small question. Nothing? Okay, with that, we will go to our final presentation from Ali Mohammadi. Ali has completed his PhD from Sharif University of Technology, and he will be presenting his research on examining the factors influencing vehicle type choice for men and women. Ali, please go ahead and share your screen.
Hi, everyone. I hope you are doing well. Do you have my screen now?
Yes.
Thanks. My name is Ali, and I want to present our paper. That subject is examining the factor influencing vehicle type choice for men and women, a comparison of objective and subjective variables. Our research problem is that we want to see the effect of the significant variables on vehicle type choice, because as we know, the vehicle type has a undeniable effect on fuel consumption, air pollution, and the severity and the type of accidents. For that, we want to determine factors which are significant in vehicle type choice. Moreover, in this travel behavior, we want to see, is there a difference between men and women in this travel behavior, because in the literature mentioned that lots of travel behavior between men and women are different. Our research question is that is there a significant impact of subjective variables on vehicle type choice? We want to add some subjective variables, for example, some attitude, lifestyles, personalities, and these types of travel behavior, because in the literature, most of the variables that was measured were objective variables, such as built environment characteristic and social demographic. Moreover, we want to see other significant difference between men and women in this travel behavior, and we want to see if we had a pooled model or see this separate model in this travel behavior, which of them is more better. The research importance is the crucial concern of vehicle type choice that have a significant impact on air pollution, fuel consumption, and safety. Moreover, we want to see the macro scale impact, which vehicle type choice has a macro scale impact that provide valuable insight for automobile manufacturing companies. And if they know the market share of each type of vehicle they produce, they can have better policies for production efficient types of vehicle. And moreover, we want to see it has a macro scale influence that informs transportation policies that they want to control and apply some better policies in this travel behavior. The literature review in this topic was started in the 70s decades, and numerous researchers worked on this topic. Most of them categorize the vehicle type choice based on based on size and function. For example, they see the vehicles as mini, large SUVs, and these types of studies continue until today. But we see the most of these studies focus on the effect of objective variables. As I told, they are socio-economic factors and individual characteristic and built environment. And we observed just the subjective variables was estimated and was seen on the study of Mukhtarian and Cho in 2006. And some subjective variables such as attitude, personality, and lifestyle was examined, and they found there are significant impact on this travel behavior. Literature gap that we try to fill was we want to add some subjective variables that before us nobody see in the literature, and examine their effect on this travel behavior. For example, we want to add some new personalities, some new attitudes, for example, safety attitudes and residential attitudes, and see are there any significant relationship between these types of subjective variables and the vehicle type choice. Moreover, we want to investigate are there any difference between men and women, and is it better that we investigate a separate model for this group of people, or we have a pool model for both groups of people. So, as I told, our research objective was to examine of diverse factors, analyzing of objective, subjective variables and vehicle type choice. And and our study was done in Iran, because today in Iran we have more than 500 types of model and a diverse type of vehicle, and people have plenty of choices to select their types of vehicle. And Iranian women today have we observe surge in women's education and aspiration of freedom, women life and liberty movement. And for that, we want to, our study was done in Iran. The data that we used for this paper, in this study, collected 3 types of data. The first part was relating to designing a survey, and we collected data by interviewing people, and more than 700 people was a face-to-face interview, and we collected data, and exactly the 731 people fully answered the questions. And moreover, we merge our data by the data that collected with the manufacturing of vehicle type companies, because we want to know, is there a difference between vehicle types? And moreover, we use some data that was collected from the Atlas of Tehran that was related to the built environment characteristic. And we want to see, is there a difference between the built environment characteristic of people in their homes and their work location. As you can see in this figure, the pooled sample was 731 people, individual, and we categorized the types of vehicle in 7 categories. 50% of a vehicle was mini. As 5 categories of vehicle was based on vehicle size, and there was mini, compact, medium, large, and SUV. But 2 categories we added to them based on their function, and that was pickup and motorcycle, because in some references that mentioned that motorcycle is a group of vehicle. But when we see the types of vehicle based on different groups of people, men and women, we can see the men have all choices, but we couldn't see 2 types of two groups of vehicle in female choices. Actually, in Iran, the Iranian women do not have a permit to select motorcycle, and they cannot get driving license and drive it. Moreover, because the pickup is uses more for carrying the cargo, none of the female and the women choose the pickup vehicles, and the female choices it has only just 5 groups. So if we want to summarize our data is categorized in 2 groups: objective variable and subjective variables. The objective variables was the individual attribute, built environment characteristics of both work location and the residential location. We see also the mobility, the primary purpose of vehicle usage that we cannot see in the literature, that nobody examined the effect of primary purpose of vehicle usage on vehicle choice. And moreover, we see the vehicle payment and usage on this study. The subjective variables was categorized in different groups: transportation attitude, safety attitude, residential attitude, vehicle attitude, lifestyle, personality, and previous vehicle satisfaction. We collected data first of all, and then by a factor analysis, trying to consider and extract some latent variables in this group of subjective variables. The method that we use in this study was first we should try and select our model. We use the multinomial logic model, but because there are different, we want to see the effect of different groups of people, we use the Bonforny multiple comparison test and try to see is there any significant relationship between each types of factors and each group of vehicle types that we try to make and estimate the initial model, and after that by finding the significant variables. In the next try, we try to improve our model and find and make the final model. And for analyzing and assessing the difference between this group of people, we use the method that was proposed by Koppelman and Chandrabat. We use the likelihood ratio test that was we want to employ and try to reject the null hypothesis that both gender share have the same choice function. After that, for each model, all parameters should have a significant relationship, and the relationship should be more over logical coherence. And after that, we should try to see a reasonable relationship between all parameters and the choice set of men and women. Our result showed that the null hypothesis was rejected and the chi-square test was 17, and based on the table that was proposed in this regard, we can reject the null hypothesis, and we see that if we have we estimate the separate model for male and female, our result would be better than if we have a pool model. I should mention, in the pooled model, we consider the different choices of between men and women, and we estimate multinomial logit model by different choices for men and women. By this model also, the separate model has a better estimation. The result of model shown in this figure, in this table, and you can see some subjective variables only just significant in male choice, and some of them are significant in women choice, and both some of them have a different effect in men and women choices. For example, I want to mention some of them. For example, the paratransit attitude, which show that people who like to use more transit instead of vehicle types. In the male choices, these people are trying to, with a higher probability, choose motorcycle. I should also mention that in both models, we select the mini vehicle and the as a base choices, and the other choices was selected, was estimated in comparison the base choice of mini. We can see the motor choice in the male choice set with higher probability we selected if people have pro-transit attitude. But this type of choices, it doesn't exist in the female choices. Another variable was that if people was irresponsible, for example, as a kind of vehicle attitude, irresponsible attitude in vehicle type, in the vehicle attitude latent variable, it means that people fuel consumption is not important for people fuel consumption or air pollution. And we can see the male who has irresponsible attitude with higher probability choose SUVs that have more fuel consumption in comparison to other types of vehicle. But these types of attitude, it's not significant. We cannot see that it has significant impact on female choices. Other types of variable was mentioned in this paper. For example, lifestyle, personalities, and moreover, the vehicle satisfaction. Another example was, for example, if people have previous vehicle was compact and they want disappear from dissatisfaction from the appearance. For example, their size was, there was dissatisfaction from the size of the compact vehicle. We can see the male with the less probability choose compact again, but women who has these types of experience with higher probability in the next vehicle type choice, they use large vehicles. And moreover, in the objective variables, we can say, for example, the man who have a work purpose and they want to use vehicles for their work, they with higher probability they use pickup and motor. But these types of factor, it doesn't. We cannot see it has significant and in women choices. But for example, the education purpose is only important for women. And the women who want to use the education vehicle for their travel to school or university, they with higher probability they use compact vehicles. And the other types of objective variables are social demographic variables, and the last one is the objective variable is built environment characteristic, and accessibility from home. I should mention that in the categorizing the built environment characteristic, we use the categorization that mentioned by the server in the literature and see the effect of population density, residential density, job density. and accessibility to work and from home. And see, for example, the accessibility from home to some facilities, for example, CBD or nearest commercial center, or for example, another, the accessibility from a home to parents' house is significant and important for women only. But for men, the work location and accessibility to work location, it has a significant impact on the type of choice, type of vehicle was chosen by men. In this regard, we have two policy implications, and that the first one is if we see the effect of subjective variable, it causes we have a better estimate from the objective variables. It means when we ignore this effect of subjective variable, it can cause that we overestimate the effect of objective variables. And when we want to put some policies, it causes that we overestimate the effect of these types of variables. If we try to add lots of and more subjective variables in our models, the first effect is that we could have a better estimation of objective variables and a better estimation. And in the step of policy implication, we estimate their effect better. And other policies that we arrived in this study was the supply management instead of demand management. It doesn't a direct policy that we arrived to that from the it's indirect policy from the result of our model, because we see in the examining of data, we saw the vehicles that produce in Iran are more air polluted and they have more fuel consumption. And we propose, if we try to import vehicles from the foreign countries, actually it could help people to have and select better vehicles and decrease the externalities of these types of travel behavior. And in conclusion, I want to say we found new objective and subjective variables that both were we identified they are significant in vehicle type choice, and see if we have separate models for men and women, we can have a better insight from the significant variables on this travel behavior. And lastly, the observed behavioral pattern in Iran exhibit market divergence from model typical of developed countries. Thanks for your attention. And if you have any question, I'm ready.
Thank you for your great presentation. Ali, is there any question for Ali?
Yeah, I was just querying about after analyzing so much of data, which vehicle you will suggest for both the genders, in which their behavior will be much more similar like for the men and women. Which vehicle will you suggest?
Actually, if I want to summarize our result and propose one of the model, it is opposed to it's opposed to our expectation, because maybe we believe that the mini vehicles are less polluted and they are less fuel consumption, but actually in Iran it wasn't. We couldn't see that, and the small vehicles, the motor vehicles, the pickup, they was more polluted, and we want to suggest that people should use more larger vehicles, such as large and SUV vehicles. That both of these types of vehicles are imported to Iran and they are not produced in our companies.
This vehicle is allowed to be driven by both men and women?
Yes, of course. Yes, okay. Both of them.
Yes, yeah. So there is a difference between the types of vehicles. So SUVs are largely, vehicles that are from Toyota, Hyundai, such vehicles, and small vehicles are produced in Iran, and they produce more emissions. So did you observe that women are more prone to more environmentally friendly cars, or men?
Actually, none of them are attending and have attending to these types of behavior. For example, if let me to show you. For example, we have in the vehicle type and in vehicle attitude, we have irresponsible, and it has just a significant impact on the type of SUV for people, for men. But more some other variables, such as, for example, joy, or or in the lifestyle, for example, presumptuous, have a significant impact on the type of choice, the type of vehicle that a woman chooses in Iran. It means that people do not have a significant, a considerable attention to build the environmental attitude, and they just, I told you, presumptuous or showy attitude, lifestyle. They have a more role in the vehicle type choice of women.
My understanding is that income level is mostly, income level defines all these things. So the ones who have a higher income prefer to have SUVs, which are, more visually beautiful, such things, and vice versa. So I had another question too. So you in your objective variables, you had different trip purposes. So each vehicle can be used for different vehicle purposes. How did you define that? Did you ask them that they're mostly using it for recreation or work or something?
Yes, exactly. Yes, exactly. I asked them. I want to say in the survey to order the types of purpose that they want to choose. They buy and they use their vehicle. And after that, we select the first answer. That was the answer was work, education, shop, recreational journey, and the others. And we see the first answer in the model.
Mm-hmm. So there are some people who use their car only for recreation purposes.
Yes,
so.
Yes, exactly. The large vehicles for men and the SUVs for women.
Okay, and there is another question, but we are over time, 11 minutes. Ali asked, did you look at other personality categories?
Yes, yes, exactly. There was more than 6 and 7 lifestyle, but none of them I cannot say on any significant relationship between them and vehicle types. Just 4 of them I can find significant relationships. All the lifestyle categories are mentioned in the table, the paper.
Okay, thank you so much everyone for attending this session. Dr. Pat Mokhtarian will talk about telework with selection model and panel data tomorrow morning. Don't forget to attend tomorrow's presentations too. And
tell your friends.
Yes, of course.
Our recording, so we do get to share these in a couple of weeks on YouTube, but I know that's really hard to do. It's a little bit easier when it's live. So thanks, everybody.
Thank you so much.
Thanks, Fatima.
Thank you, Dr. Cook. Bye.
Thank you, everyone.
Hi, Poria. I know you can't unmute yourself. Woo. Aditi, thank you so much. We got to get you a photo associated with your Zoom account so that we could see your lovely face. And of course, you can always show it because you are one of the hosts.
You're welcome, dear Dr. Mohammed.
Hi, Ali. Oh my gosh. Ali doesn't sleep. He just doesn't sleep, people. He's in Iran and he was in the Eastern sessions last night for me, which was really early for him in the morning. He was speaking.
Yes.
Okay, I'm checking out. Osama, nice to hear you. Bye, guys.
Thank you. I'll see you.